In this video, we'll be going over example 11 from the note packet. If Michael Jordan had a vertical leap of 1.29 meters, then what is his takeoff speed and his hang time? So we're asked to find two things, the takeoff speed and the hang time, where the hang time is the time that it takes for him to go up and then return back to the ground. We're also given information that he can jump 1.29 meters up in the air, so that's his maximum height in the air. This is a free fall type problem since we're dealing with that hang time. The first thing we're going to do is we're going to define a coordinate system. So I'm going to call the upwards direction the positive y direction. To the left here, I've already drawn a motion diagram for the upward portion of the motion. And so the spacing between the dots is getting smaller because he has an initial velocity in the upwards direction. That's that takeoff velocity. And we have acceleration in the downwards direction as a result of gravity. So since we have opposite directions for acceleration and velocity, we are going to get a slowing down and hence a closer spacing of the dots. I can now start filling in the information into the motion diagram. So spanning the entire motion, we don't know how long this upward motion is going to take. So we're going to put a question mark next to time. We do know that the acceleration is in the downward direction as a result of gravity, so it's negative 9.8 meters per second squared. The first dot in the motion diagram, we're going to call that a position of y is equal to 0 meters since we're starting from the ground. And we don't know what the initial velocity is because that's something that we're looking for. For the upper dot in the motion diagram, this is going to be the final position, and it's going to be corresponding to the maximum height that he can reach. So that's 1.29 meters. The velocity all the way up to the top is a turnaround point. So he jumps up, he reaches a maximum height, and then he comes back down. So the velocity must be 0 at the peak of the motion. So we have a final velocity of 0 meters per second in this top dot right here. For the downward portion, the motion diagram would look exactly the same, except as he's going down closer to the ground, his velocity would be increasing, and that reflects the increased spacing of the dots on the way downward. The downward time would have the same time that it takes for him to go up. So the total hang time, T hang, is just going to be equal to 2T up. We've been asked to find the hang time, and we expect that to be positive and in units of seconds. And we're also asked to find the takeoff speed. So that's the magnitude of the initial velocity. We expect that to be positive and have units of meters per second. Since time is not a known quantity, we'll use the kinematics equation that doesn't have time to be able to solve for the velocity, initial velocity first. So that'll be our first equation. And that is the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. After we use this to solve for the initial velocity, since we know the final and we know the acceleration and the displacement, we can use that and substitute in to the velocity as a function of time equation, which is the final velocity is equal to the initial velocity plus the acceleration multiplied by time. And we can use that to solve for the time that it takes for Michael Jordan to go up. Then we just need to multiply by 2 to get the total hang time. So we know the final velocity. We don't know the initial velocity, but we can solve for it. We know the acceleration, and we are looking for the time. So 2 equations, 2 unknowns. We can solve for both. So I've gone ahead and worked through the algebra already, and I started with the first equation from our plan, the velocity equation without time involved, to solve for the initial velocity. Substituting everything in and taking the square root, we get an answer of plus or minus 5.03 meters per second as an initial velocity. We choose the positive value because we want a takeoff speed in the upwards direction. And so the way we defined our coordinate system, we want the positive direction since we want to be going up. Since it asks for the speed, we need to take the magnitude of the velocity, and we find that to be 5.03 meters per second. After solving for the initial velocity, we then can use the velocity as a function of time equation, which is equation 2, to be able to solve for the time that it takes to go up. Substituting everything in, we find that that time is roughly half a second, but that is the time that it takes for Michael Jordan just to reach his maximum height. We want the total hang time, so that's twice the time that it takes to go up, as we previously discussed, and that's equal to 1.03 seconds for a hang time. Now we need to check our solution just to make sure we didn't make any errors. We found both of the quantities we were looking for. The signs are both positive as we anticipated. We have meters per second for speed and seconds for time, so the units look good. And is the magnitude reasonable? A 1.03 second hang time is probably high for the average person, but since Michael Jordan's a professional athlete, a second seems reasonable for how high he's able to jump. So we can check off that last one.